talk to you today about why this job is too hard. And because I've spent a lot of time in a variety of venues talking about Kubernetes and talking about containerization, I profoundly believe that the moment that we have reached now, where Kubernetes has become a commodity, first of all, is amazing to me. I still, 4 years later, am shocked. But it's really the beginning. And so I want to talk today about why I think of this, everything that we've built so far, and honestly everything that you all are doing who are deploying Kubernetes in production, as the initial stages of what I hope will really dramatically change the way that we approach building distributed systems and building cloud-native systems. Because I think we're really only scratching the surface. And as the title says up there, the job that you are doing today simply is too hard, and there are too few people who know how to do it. All right, so what is the job? If the job is too hard, what is the job? Well, the job is to build new releases. Maybe it's to build new features, to do weekly, sorry, confuse those two. Yeah. Build new features. Somebody's saying, hey, you know what? We need this feature in the app as soon as possible. Our competitors just added it. A big customer asked for it. Whatever the reason, we need this feature out. We need that weekly release cadence or maybe a daily release cadence. We have to be shipping features constantly. You have to have perfect uptime, right? I don't know how many people remember, but it used to be that you'd log on to a website, a bank website or wherever, and it would say, you know what, from 11 to 12 at night, we're going to be offline for maintenance, whatever that meant, usually schema upgrade. But now, every time I see those, and every once in a while I run across a site that does that, it is shocking to me, right? I am here in Europe, my bank is in America, I'm going to be using my mobile phone to access their APIs, and I expect them to be up and operational, right? So in addition to shipping new features, constantly releasing software, you still also have to maintain perfect uptime. And then there's this constant pressure, and I'm sure that you feel it and I feel it, like there's always a new thing to learn about. And is it a new thing to learn about because it's a thing, or is it a new thing to learn about just because someone has a buzzword that they would like you to use in their slides, right? And so I think not only are we thinking about shipping features, not only are we thinking about maintaining uptime, but we're constantly absorbing new technology and figuring out whether or not it's a useful thing or whether it's just the newest thing. So in order to achieve this job, what are we using? What are we using to put this together? Well, we have patterns and practices that we've all learned, and we learn from our colleagues, and we learn from environments like this. There's a degree of infrastructure support. Things like Kubernetes help make this job a little bit easier in some respects. We do a lot of code reuse. I think this is one of the big revolutions from maybe software development of 30 or 40 years ago, is that suddenly we get to share a lot more code. Networks have helped with that. Software languages that were organized around sharing code, sites like GitHub that are organized around sharing code have helped with that a lot. And then using tools like Hacker News and other sorts of sources to find out what's going on, what are other people doing, what is the, I would posit a guess that you all found out about things like Docker and Kubernetes even from these sorts of sources where you read an article, you heard something interesting, you went to a conference, you learned a little bit more about it, you tried it out. We slowly accumulate all this information. But the approach that we're taking with all of these tools is we have to learn everything. You need to know from the top of the stack all the way down to the bottom of the stack how everything works. You have to build everything by and large, right? I find, and whenever I talk to people about how they build their systems, I find that they're all building the same thing over and over and over again. Sometimes themselves, each new app builds the same things over and over again. I found this in my own life, building systems. I knew what to do, but I still kept re-implementing things. We don't have enough libraries. We don't have enough shared code. Despite all the shared code that we've built up, we don't have enough shared code around distributed systems. We have to teach new people about how the system works, and we have to teach people about how our system works, which is different than someone else's system. Even though really they're the same, when you squint at them, they look the same, but none of the knowledge is transferring forward. And we just keep doing this over and over and over and over again. And I think that, I don't know, for me anyway, I have reached a place where it feels useless. It feels sort of like wasted effort that I should be spending building a better application, spent re-implementing things that I already know how to implement, right? And I don't think we can keep doing this, right? Because the pressure of releasing new APIs and the pressure of releasing new features, it's only getting worse, right? Every new, it used to be okay to do a monthly release. Now it's not even okay to do a weekly release. I think there will be this expectation of a feature request can be posted to a forum, in the morning and available in the mobile app in the afternoon. And that's where we're headed if we're not there already. And so I really profoundly believe that while we've built up a lot of interesting tools, we have not built up enough to achieve the goals that we have, that are coming down the pike or that are even here today. But the valuable thing about the world is that history continues to repeat itself. I find myself, we were just talking earlier, Adam and I, about sort of the sense of history that you have when you come to a place that's been around. And I think even though the computing history doesn't go back that far, we can look to the history and say, if we're in this space where it is too hard to build all of these systems that we're expected to build and at the cadence that we're expected to build them at, well, this must have happened before. And in fact, it has. And I would argue that it's happened at least twice before. And if you stretch back, maybe you can come up with other epochs as well. So what happens in general when the job gets too hard in computing and in technology? We build tools. We build better tools. We find patterns that we can have commonality around and build shared implementations around. And so if we think about history and the historical reference points, I would argue that the very first moment when the job got too hard was when suddenly people realized that people who weren't literally building the machine needed to be able to program the machine. And people who weren't necessarily mathematicians or the early computer scientists of the day needed to be able to write code. Right? Needed to be able to express ideas and build applications because they were subject matter experts in a particular area. And out of that comes Fortran, right? Out of that sense of we need a thing that is better and more expressive and easier to use than machine code is Fortran, right? It is literally about taking formulas and translating it into machine code. That's Fortran. And then at the same time, the patterns start to emerge, right? So the minute you have a computer programming language, suddenly people start thinking about abstract algorithms. You're freed from the literal machine code to think about the abstraction. And from the abstraction, you have the development of the idea of an algorithm, right? Knuth writes this book, and it isn't even grounded in anything that you can execute. But it tells you how do you sort things. It tells you, it canonicalizes this set of programs that people were writing over and over and over again. You still have to write it, but at least you can read the book and basically understand the way that the algorithm is supposed to be, and we can collaborate and build better sorting algorithms, right? Over time, we can analyze those algorithms, and we can find the ones that are best, right? So I think this is the first time when the job got too hard, and we built tools, and we found patterns to make it easier. I think, again, in the 1980s, this happened, where suddenly software was really starting to eat the world, and building software in large teams became a very important part of many businesses. Right? And I think what happened in that moment is that it turned out that software wasn't scaling. The teams got too big, communication was hard, the people who were programming maybe weren't the best programmers, and they weren't deeply tied to the machine. And so as a result, coming out of that, as we see this rapid growth in the lines of code written, you see object-oriented programming come to the fore. You see Java and C# managed environments that kind of shave off a lot of the hard edges from programming to the machine come into the mainstream, right? And at the same time, you have this emergence of the design patterns books, the most famous being the Gang of Four book. Eric Gamma et al. Wrote around software design patterns, right? And I think that was really, again, technology and tools advanced, patterns were recognized, and suddenly we started thinking about object-oriented patterns, and we started thinking about ways you could structure your software to make it more reusable. And I think that's really also where the library revolution came out of. Without C++, without object-oriented code, without managed code, I don't think you have the degree of shared libraries that you do today. Although the network is important as well. So I think the third phase that we're in right now is this notion of reliable distributed systems. Right? I have this interesting discussion with some people who develop IDEs and things like that around the fact that the crux of what we do has changed. It used to be that the crux of what a developer did was build a GUI that had some business logic behind it that might have been connected to a database. Right? And now we all build APIs. And we all build APIs that are distributed onto the cloud, onto multiple machines, that have and now we're starting to think about, well, let's take those APIs and turn them into microservices. We're at this moment where designing and distributed systems is the problem of the day that has become too hard. Machine code's not hard because we have programming languages. Scaling our software, it's tricky, but it's well understood, and we have languages that help with it and techniques that help with it. But now distributed systems is the thing that has made the world too hard. And what we've found is the tools are starting to emerge. In Docker and in Kubernetes, the tools that you need in order to work on this are starting to emerge. They're not done yet. The patterns, I think, are still evolving. I think we're starting to see the canonicalization. If you looked at the dates in the previous two examples, the patterns books tend to lag the technology by 5 to 10 years, if not even a little bit longer. It takes a while for us to figure out what all of the patterns are, but I think we're starting to talk about that, and we're starting to see what some of the things are, and that's a really valuable moment in time, and I really encourage you all to participate in that discussion. All right, so taking a look at the solutions that we have out there. Well, historically, the solutions have been things like compilers, debuggers, unit testing, integrated development environments. These are the kinds of tools that you think about. Now, the sad part about this is that all of these tools are about building programs on a single machine. None of these tools help you build distributed systems. And I think that's where we're at. So people asked about containers, people asked about Kubernetes. How many people do print line debugging? That's slightly lower than I would have expected, actually. How many people just don't debug? I would argue that in the space of software tools, actually, I do print line debugging, by the way, constantly. Even in unit tests where I shouldn't, which shows you how Stockholm Syndrome I am. But I would argue that the apex of development tools actually was in client server around 1998. Right? And that's kind of sad that we got kind of stuck. We actually maybe even went backwards a little bit as we've moved into distributed systems. We need to start thinking about broadening the space of tools that we're building. It turns out we're starting to, and that's good, right? And so with tools like Helm, which is a package manager for Kubernetes that allows you to sort of package up and use distributed system as off-the-shelf software, the same kind of approach that allowed you to do apt-get install MySQL now allows you to install replicated MySQL onto a Kubernetes cluster. That's great for that off-the-shelf side of the house. We're doing a lot of work in building an extension for Visual Studio Code that integrates you with Kubernetes. Draft is a tool that I'll show in a little bit that kind of tries to help people learn, because one of the other problems is all this complexity happens. The on-ramp gets steeper and steeper. There's things like telepresence that are really interested in how do I take the services that I'm building in the cloud and yet project them down onto this laptop where I'm doing all this developer work? How can I make my development environment and my cloud kind of work more seamlessly together? The new version of Jenkins that's out there is targeting Kubernetes natively and is really taking on a lot of these tools as its native environment. Same thing as Spinnaker did earlier. So we're starting to see these tools develop. And to give you a sense for what this means, I want to give you a little bit of a demo of some of these things, right? So the first piece is this visual work in Visual Studio that I and the team have been working on a bunch recently. So I'm going to drop out and go over here. So what you'll see here in Visual Studio, I have Visual Studio up, that looks pretty legible, is I have the extension installed, and I have this little Kubernetes dropdown. And when I open up the Kubernetes dropdown, what you can see here is it's populated with my clusters that I have configured, right? I'm not going to tempt the demo gods by using something over the network, so I'm going to use my local Minikube cluster. And when I see in there, what I have is just like you have a tree view for your source code, now I have a tree view for my Kubernetes objects, right? And so I can go in and I can say things like, oh, hey, what's the namespace that I have here? Well, I have these three. I'm going to actually switch. I'm going to right-click. I'm going to set kube system as my current namespace. And now I can go into my workloads, take a look at my pods maybe, and I see all of the pods that I have running. Or I can look at my deployments, and I can actually see the deployments, and then I can actually drop into the deployments and see the pod that is part of that deployment, right? So now suddenly, instead of having to use a command line tool, which requires you to both switch context from the code that you're working on to a different context, as well as, honestly, a command line is great for scripting things, but not as good for visualizing things. Now I have a more visual, more integrated environment for exploring my cluster, and I can even do things like come over here to this pod and say, okay, well, you know what? I would like a terminal in that pod. I'd like to log into that pod. It's going to ask me which of the containers in that pod that I want to connect to. I'm going to select the kubedns one. And now over here in this terminal, I'm there inside that pod, right? So I think this is nothing, by the way. This is all just the Kubernetes API under the hood, right? There's no magic that's really in the IDE. It's really just the integration of these things into my development environment that enables me to have easier access to both the thing that's in the cloud as well as the source code that I'm developing on my local machine. Right? So I think this kind of bridging between the act of developing and the act of deploying is the area that we need to work on the most. Right? It used to be that code and application were naturally close together because the code and the place where the code ran were the same machine. The place where the code runs is now very far away. We need to think about how we can use our tools to bring them back together. So the next tool that I want to show you a little bit example of how we use this is this tool called Helm. So if you saw before, if I drop out of the Kubernetes environment, close my terminal, there we go. I have a little simple Node.js application here. So this is a really, really simple web server written in Node.js. Something that I think someone with a little bit of JavaScript experience and a little bit of web surfing could easily come to, have kicked together in an hour, say, or less, really, if they just cut and paste. But now you say to this person, all right, great, fantastic. You've written a web server. You can run it locally on your machine. I'd like you to run it in a Kubernetes cluster on the cloud. And they say what now? And you start saying, oh, OK, let me explain how to do this to you. Well, it's actually too much to explain, right? I don't think that you want to initially, and we'll talk a little bit more about this later, I don't think you want that person to immediately have to learn all this YAML and all this sort of stuff. You want them to be given steps forward, but you want them to be able to get to a point where they're successful quite quickly. And this is really where Helm comes into play. So if I cd into that directory, I can actually say Helm, which is this, sorry, not Helm. I said Helm. I meant draft. I'm sorry. So please rewind the last 2 minutes of me talking and replace Helm with draft. Can we do that on the video? That'd be great. So what draft allows you to do, actually, is to scaffold all of this stuff, right? So if I look at the draft tool, it has a whole bunch of commands, and it actually has a component that runs inside the cluster, which is actually already present. But draft has the ability to, so you see right here, draft create, transform the local directory to be deployable to Kubernetes. Right? So now I can just say draft create. And what's going on is draft is detecting the language that I'm using. It detects that this is a Node.js app. It has some templates around how to build a Node.js app. And it's laid down two things. If I go back over to my directory structure, you may have seen it come in. It's laid down a Docker file. And it's laid down a charts directory. And inside the charts directory, you can see that there's this chart.yaml file, which describes a Helm chart that you can use to deploy your app. And now, just by running draft create, now I can run a Docker build, I can run a Helm up, and my application is deployed to Kubernetes. Yeah, I could do draft up too. That's true, actually. Either Helm, because I have the chart, either one would work. And draft up is even easier. Draft up will actually upload your code and do the build for you. Right? And so I think that the whole point of these tooling is let's use something like the VS Code extension to bridge the code in our machine to the code where it's running in the cloud, and a tool like draft to smooth the path from the code on your machine to the code running in the cloud. All right, close my recommendation there. All right, I'll jump back into my talk. All right, and that's draft. All right. So in addition to thinking about how do we make it easier for the code to get into the cloud, one of the other things that's happening is we're thinking about ways to make the cluster more automatic. Right? So a lot of the time when we think about what it takes to deploy an application into the cloud, there's a lot of ancillary stuff. How are you going to monitor it? How are you going to restart it? How are you going to find out, what certificates that need to be rotated? All of these sorts of the pieces that are the cruft, if you will, or the essential extra components that are the difference between a piece of code running one-off on your machine and a reliable piece of software running in the cloud. And so I think one of the powers of Kubernetes and one of the powers of this cluster infrastructure isn't just that you can deploy your containers there. It's that it actually becomes an environment where you can make things things like monitoring be automatic. And this is where cluster services come into play, right? So with cluster services, it allows a team that maybe understands a particular area that to deploy a solution that works across every single application that's deployed into that environment. So we can have cluster-wide standardization of these services, things like logging, things like monitoring, things like intrusion detection. Application developers simply get them by deploying into that environment, and so when they run draft and they deploy their application into that Kubernetes environment, suddenly every single thing that they write to standard out goes into a log aggregation server that is searchable and stored for 90 days or whatever your logging period is, right? That's hugely powerful. You didn't have to teach them about it. They just wrote to standard out just like they were used to doing on their machine. And when it came time for them to do introspection of their logs, they were up in a search index that you could show them how to access. This sort of just-in-time learning with actual, it's not just-in-time learning so I can learn how to deploy monitoring. It's just-in-time learning to tell you, oh, by the way, it already had happened for you, is hugely empowering to application developers and only happens when you have that cluster infrastructure. And more importantly, also for people who are thinking about monitoring, the truth is that if you're an SRE, monitoring looks an awful lot like this, right? 3 development teams. One development team says, you know what, I'm going to use statsd. I've been around for a while. statsd is awesome. Another unit says, hey, you know what, I'm going to use Prometheus. And the third team says, monitoring? And the SRE says, I think I'm going to quit. Right? And it's because there's this inconsistency in the environment because you've allowed this choice to be made by the end user. Right? And so by standardization, not only do you make it easier for the end user, you actually make it easier for the operator as well, right? And I think this sort of win-win, this sort of virtuous cycle is the good thing that has happened in this environment where we're starting to see the tools be developed that aren't opinionated just because somebody has an opinion, but they're actually valuable because they make life better for every single person involved, right? And I think that's why you see this rapid adoption of containers, Kubernetes, and other technologies, is that there is value in it for every single participant in the playground. So this is basically what it looks like. You have a cluster-wide monitoring solution. You have the Kubernetes API server. User comes along and creates pods. Cluster-wide monitoring looks at the Kubernetes API server, discovers that those pods have been created, and starts monitoring them automatically. Starts scraping the logs out, starts scraping CPU information and everything else like that, and eventually pushing it out to a cloud monitoring or some other monitoring solution that you've developed. Right? And again, this is all automatic. The user wasn't involved in any of this. The cluster administrator is the one who's gone about establishing this stuff. All right. So I think that gives you a sense for the tools that I see people developing. There's lots more, of course. I could spend hours actually expounding on the various tools that people are building to help with the deployment of distributed systems. But I think that although tools are very useful, they are insufficient, right? And so what else is happening and what has happened historically is the development of patterns and libraries, right? So over time, we saw the evolution of things like POSIX. Used to be that there wasn't a standard for application programming on Unix, and then the POSIX standard came along. Things like npm install, right? We just have this expectation that you can use npm install literally almost whatever you want, right? Things like unit testing, it's a pattern and a library, right? We expect unit testing frameworks. We understand that unit testing is an essential part of software development. And then also these extensible libraries of patterns, right? Like how many people have implemented sorting after they left undergrad? It's not very many, I hope, right? You shouldn't be implementing sorting, and yet everybody uses it. Everybody knows that this is something that you should do. Same thing with HTTP clients, right? Like we've reached a stage where if a language doesn't have HTTP built in as a native library, you don't even understand why someone would bother, right? Like that's the level of expectation around both libraries and services that we have in our programming language environment. And so we're starting to see these things develop as well. So there's a tool that one of my teams at Azure has built called Brigade, which expresses things as a workflow. There's things like Service Mesh with Istio and Linkerd and many others being developed. There's things like Hadoop and Spark, and PaaS that is being built on top of Kubernetes so that you can consume functions as a service, you can consume other PaaS patterns laying in on top of Kubernetes. To give you an example of how this works, think about the act of setting up some code to run a build that runs every single time you push code to GitHub, right? Now, fortunately, there's software as a service things that make it easier for you to do this. Check in a YAML file and magic happens. But if you have to do it yourself, This is a bit what it looks like. GitHub sends an event, there's an event listener, and it runs a build script. In Brigade, this is how you would express that, right? Again, getting back to meeting people where they were, allowing them to take a little bit of JavaScript and turn it into a workflow. I can say things like, hey, you know what? I want to create this source for events. I want, when there's a push, I want to run these tasks, make dir, copy, cd into it, do some go get, do some ensure, and run my tests, right? So now I've just expressed a workflow, a continuous integration workflow based on GitHub pushing, written it down in a piece of code. I can unit test this if I want to. I probably should. I can teach someone how to do this if I can teach someone how to deploy a workflow to Kubernetes if the only thing they've ever done before is front-end JavaScript work. That's hugely empowering because I can write that program, and then when it's deployed, it is containerized, packaged, and deployed out onto Kubernetes. Right? Again, building out patterns so that people don't necessarily, just like with sorting, they don't necessarily know how to implement it, but they know what happens when they use it. Right? I think most people are content to understand that if I take advantage of this pattern, somehow behind the scenes the right things happen and my workflow runs, or my sorting algorithm runs, or whatever else it happens to be. We've up-leveled ourselves by building an abstraction that I can program to. I think the third piece that we see coming out of this is the introduction of language features. Right? So in addition to tooling and in addition to patterns and libraries of reusable components, I think that what we've seen historically is that programming languages themselves have evolved and adapted to build features that are oriented to the problems of the day. Right? And the problem of the day from about maybe 1990 onward, mid-90s onward, was synchronization. Right? Multiple cores suddenly meant that threads were running at the same time. You needed to write multi-threaded programs to take advantage of multiple cores on processors. Languages evolved to adapt features to make synchronization into a first-order primitive. Right? Things like synchronized as a keyword, async await. If you haven't checked out TypeScript and used async and await in TypeScript, or if you've had experience with it, it's life-changing, honestly. Like, TypeScript is amazing. That's my little fanboy plug. But it's really like, if you find yourself caught in a stew of promises, just the introduction of this language feature, the idea that you can await something, it just changes the way you can write code, right? You can write exactly the same code in standard JavaScript. It's just easier because there's a language feature that is adapted to that environment. Things like garbage collection, even things like single threading, right? Like, one of the reasons I think JavaScript is so popular for people to write servers is, like, we can teach you about how to use locks, or we could just have a single thread and have lots of callbacks all over the place, right? It's just easier to live in a world where there aren't locks. Now, maybe there's some performance issues that come with that, but if you establish the right programming patterns with all this asynchrony, and then you introduce concepts like await, the things sort of shake out in the wash. You see these language features being developed to support solving the hard problems of the day. But again, all of these examples are things that work on a single machine. None of these things make it easier to build distributed systems. They only make it easier to build the program that runs on a single machine. Right? And so it's great that we've done all this work, but the problem of the day is multiple containers on multiple machines. We need to build a language that is idiomatic to the cloud. Right? I think I would argue with the language features I mentioned on the previous page, we began to build languages that are idiomatic to synchronization. But we need to build a language that's idiomatic to the cloud. So, and effectively, the problem is, how do I take my code to the cloud? We've talked a lot about that with tooling. And then how do I take my cloud to a distributed system? Those are two somewhat separate but related problems. I would argue that we actually have to build a system that addresses them both. Just like you go from code on one machine to code on multiple cores, code on one core to code on multiple cores, we need to go from code all the way through to distributed system in a single environment. But it's worth understanding that those are two somewhat disjoint problems. And when I say, as I said, when I said cloud here, it doesn't necessarily mean public cloud. It doesn't necessarily even mean virtual machines. It could mean Kubernetes running on physical. It's just an API-driven deployment environment, an application-oriented deployment environment. All right, let's take a look at what it takes to go from code to cloud right now. Right? If you are going from code on your machine to code running in the cloud in Kubernetes, this is what you need to do. You've got code. you have a compiler, you turn it into a binary, you have a Docker file, you turn it into a Docker image, you push it into a container repo, you write some Kubernetes config, you deploy it to a Kubernetes cluster. Right? There's at least 3 files involved in this. There's your code, there's the Docker file, and the Kubernetes config. There's at least 3 languages, your code, the Docker file, and the Kubernetes YAML. And there's at least 3 tools, your editor, whatever it happens to be, your Docker to do the Docker build, and kubectl to do the push. Now, some things, draft makes some of these things a little bit easier here and there. But honestly, there's way, way, way too much complexity here. Right? And we haven't even gotten to the distributed systems part. Right? That was just the get my code into the cloud part. Right? Or day 2. What happens when I need to roll out a new version of this? Right? There is just too much complexity in the system. We need to simplify it down, and we need to simplify it down not just with tools, not just with libraries, but actually, I would argue, with new approaches to programming and new approaches to building the software that we're developing. Because I would argue that this just doesn't, like, when presented this way, I hope that it doesn't seem okay. Right? I hope that you look at that diagram and you think back and you're like, yeah, that is what I do. And it seems okay to you in the moment when you're on your laptop because you've scripted it or whatever to reduce the pain a little bit. But when presented this way and when I wrote down these slides, it really struck me that this just is not an okay tool chain. All right, so if we're going to build a language idiomatic cloud, what are the principles that we need to use to guide this development? Well, I think I would argue strongly that it has to be a formal programming language. We have spent, I don't know, maybe 10 years or so in the world of config languages, from things like Puppet to Salt to Terraform to all of the things like the Azure templating language, and Kubernetes YAML, and Helm has its own templating language. And I think the lesson that I have learned anyway, having been involved in the development of a lot of these different languages, is that inevitably they're Turing complete. Inevitably they take on inheritance and abstraction and encapsulation and other properties of formal programming languages. And inevitably they're terrible. Right? Like, it's just like all of them are bad because we all back into them slowly because we thought that we could get away with just data, and then people ask for all these features, and eventually we build conditionals and stuff like that. I think that the truth is we need to accept that configuration is programming. Like, people are now okay with the idea of infrastructure as code. But I don't think they're quite okay with the idea that code can express infrastructure. Right? And I think that we have to get over that. And I still talk to people who are sort of like, no, it's different. And I'm like, well, I really don't think so. You can write different pieces of code. It doesn't have to be the same code. Like, you can separate the code files. But there's no reason not to just use a formal programming language. And by the way, if you use a formal programming language, you get syntax highlighting for free. You get unit testing for free. You get code style for free. Like, all of this stuff that we've developed around software development for literally like the last 50 years, you get for free. And why bother reinventing a bad programming language in YAML? It just doesn't make any sense. I think another part of this, though, is that the natural tendency here is to build paths. The natural tendency, and it's like, I'm not the first person to say, hey, you know what, it's too damn hard to deploy stuff. Right? All sorts of people have built environments to make it super easy for people to deploy cloud-scale code. The trouble is they've all been paths, and they've all been walled gardens, and they inevitably have their limits, right? 12-factor apps are great, but they don't go everywhere. Functions as a service is great, but it doesn't go everywhere, right? You have to build modular environments, not paths, walled gardens, because inevitably people will hit the edges, and they'll be frustrated, and they'll lose the code that they put into the walled garden, and that's a very frustrating experience. You only do it a couple times, and you never do it again. And then finally, it needs to be idiomatic. It needs to look and feel like natural programming languages, and I think this has to do with building the ramp, right? CS 101 person, if I took a student who's in CS 101 and I tried to teach them how to bring their code to the cloud, I have to teach them so many concepts between figuring out how to write code and getting them into the cloud and new file formats and all this sort of stuff. Like, it's a huge barrier. It's a huge barrier to entry to go from I can write code on my machine to I can deploy that code into the cloud. And then finally, it has to be open source, right? I think we've reached a level of understanding in this world that we collaborate, and for everything that is effectively non-essential to my business, it's going to be open source, and infrastructure like this has to be open source, or else someone else will just build the same thing and make it open source, and that thing will win. Like, open source just wins, and so therefore we have to do this thing out in the open. All right. We can also learn from history. It turns out, again, this is not an original idea. MapReduce got there first, right? So MapReduce said to you, Hadoop said to you, hey, if you implement these two classes, my mapper and it has this interface, and my reducer and it has interface, I'm just going to take your code out into the cloud and out to these thousands of machines, and magic stuff will happen. And it's pretty cool, right? The entire big data revolution is built on the idea that idiomatic cloud can allow people who might not otherwise be able to have access to distributed systems. I think that what happened was people got so hung up on MapReduce, they failed to recognize the fact that MapReduce is an example of a broader set of patterns for distributed systems that we should make available to people via programming language interfaces. And so we built a singleton, and we failed to see the general pattern. And I hope that now we're going to begin to start to see the general pattern. And that learning is what led to the development of this. More recently, there was this system called PiRen that was developed. And the basic idea was, hey, you know what? If you know how to do a Python map, you can do a map out in the cloud, right? And the idea behind PiRen was to take that Python code, deploy it into a functions as a service implementation, parallelize your map function, right? You didn't teach that person a single new concept. You just said, hey, take that map function that you were thinking about before, substitute in PiRen for the map function. Suddenly, you have teraflops of scale available to you. Embarrassingly parallel processing, right? This is huge because, again, if we can reduce the barrier to entry to people using the cloud, we're going to have way, way, way more cloud users out there, way more distributed systems capable people who can consume these concepts even if they can't implement them themselves. All right. So this has led to the development of a system that I've been experimenting with for 1.5, 2 years at this point, called Metaparticle. And the idea behind Metaparticle is to try and define what it means to be this cloud idiomatic programming language. I will say that this is really an experiment. It's really an aspirational statement for what I hope the future looks like. I don't expect anyone to go, don't run out and use this for production. But please do go out and play with it. To give you a sense for what it looks like, I want to take a look at what it takes to build a reliable web application. Right? So if I want to build a reliable web application, I need to do things like have a public IP address, have a load balancer, have some replicas. Right? The gulf between I'd like to build a reliable web app and this is pretty big. Right? Again, you can use platform as a service for this, but it has limitations. If I want to do this in a way that I can move forward from my reliable web app to my reliable microservices to a team of people building reliable web services, I have to learn all of this stuff. And it becomes too hard. So if we do this via Metaparticle instead in a cloud idiomatic way, I can express this in Python with this containerized directive. Right? Python has these incredible decorators. They're really, really cool. And I can actually put a decorator on my main that says, hey, you know what? I would like you to containerize this application. I want 4 replicas of it. Here's the port that I'm going to serve on. Here's the code that I want you to run. Now, when you do this and when you run this Python program, what it actually does is it packages itself as a container. It deploys itself to Kubernetes. It tails the log files. And now you have this 4-way replicated system up and running in Kubernetes. So this picture is the output of running this program. And what we've allowed somebody to do is, in a single environment, start thinking about expressing not just the code that they want to have run, but the topology and the deployment of that code at the same time. They haven't had to learn anything new. It feels natural. It feels like an extension of the thing that they were doing on their machine, and yet it's running in the cloud, it's running replicated, and it's taking advantage of all this stuff. So this is the way that it works. You can express your Metaparticle program here. There's a Metaparticle Compiler that effectively translates it into the assembly language of Kubernetes. It really approaches the problem as if saying, if my code were to be compiled to Kubernetes, what would that look like? If I wanted to compile a distributed system to Kubernetes, what does that look like? But in fact, we understand at this point that it's a polyglot world out there. And so we need to actually support not just a single programming language, but a bunch of programming languages. So in fact, the Metaparticle Compiler actually translates programming language code to an intermediary representation that runs through an assembler that takes it to Kubernetes. This means that that same program that I just showed you in Python, I can also show you in JavaScript. Right? It looks a little bit different because the idioms of JavaScript and the features of the language are a little different than the features of the Python language. But I can define, I can use my require to pull in the language, define my server. I do this containerized function because I don't have decorators. But the idea behind it is exactly the same. When you run this program, it deploys a replicated copy of itself behind a load balancer to a Kubernetes cluster. Right? So I am, again, expressing the code that I want to have run with the deployment topology that I want to have execute. And in particular, it supports, at this point, Python, JavaScript, Java, C#, Go, Rust, Ruby. And it's relatively easy. In fact, most of these are community contributed. It's relatively easy to add your favorite programming language here. And so that's, I guess, in some ways, a call to the community to say, if you want to play around with this, if you have ideas, please come and check it out. There'll be links later. But of course, it's a very big claim to say that this is, this beautiful new world. Without a demo to back that up, it rings a little hollow. And so I want to show you an example of Metaparticle in action. So we'll go over here. Hopefully that's big enough. All right, so here's that code. It's actually a little bit, I had to shorten it to get it into the slide. So there's a little bit more, like the Docker repository, the fact that I want to publish it, the fact that it has a public IP. But you can see that this containerized directive with some options and the code that I want to have run is basically, here are the options here, and the code that is actually running here. And now when I actually execute this, you can see I just say node index.js. You can see it's actually building the application, right? So in the background, you see the Docker build. Now it's doing the Docker push. And in a second, it's going to deploy that out to the Minikube cluster that's running on my machine. And at this point, it's tailed the logs. So you can see the 4 replicas there, that it's tailed the logs, and it's bringing the logs down to standard out. So what's important here is that the experience of running this code actually feels like the experience of running it on my machine. If I print to standard out, it comes to standard out on my machine. Obviously, in production, this is not how you would go and deploy this code. And I'm not even sure that Metaparticle is useful for production. It really is about taking that developer from code that's on their machine to code that's running in a distributed way out on the cloud. You can see the output from the various servers. I'm going to connect in. You can see here the services that are running. Actually, this is what happens when you do multiple demos. Those were the services from the Cube system namespace. But if you get the deployments, you can see there's my 4-way replica of the deployments. And now if I actually go and get a shell inside that Kubernetes cluster, it takes a second. I can actually say wget dash. And you can actually see there's the output. You can see actually in the logs, there's my request coming through. And I can change this to, and you see the same thing coming through. And you can see actually there that the replica's changed because it's behind the load balancer. And so I hope that shows you how, with a fairly straightforward piece of code, I actually went and deployed a replicated system, a simple replicated system. All right, we can kill out of that. And in fact, actually now, as I hit Control-C, it's actually tearing down that application. So really, the aesthetics of running a program on your own machine matches the aesthetics of running that program out in the cloud. All right, drop back into the slide deck here. But it turns out, actually, that if you allow a programmer to do this, the minute they distribute their application, they suddenly have to learn about synchronization and distributed synchronization. It's a big problem, actually. It's one of the biggest hurdles to getting into a distributed system. And so in addition to allowing people to replicate their code, I think it's very important that we allow them to easily consume concepts that allow for synchronization between the code running on multiple machines. So we actually also, inside of Metaparticle, introduced the notion of synchronization. This is a Java example of a synchronized lock. The lock actually looks just like the interface that is there for a Java lock, but in this particular case, this Metaparticle lock will do synchronization across multiple components that are running on different machines, running in different containers. We do this because we know that we can deploy to Kubernetes. We know that we are deploying to Kubernetes. We can define a custom resource inside the Kubernetes API server that can be the lock that we acquire. And I can use a sidecar to do most of the implementation of the locking to give me a simplified API that I can access from my application code. This means that I can share locks between Java and Python or JavaScript and Node, or sorry, JavaScript and Go or anything else like that, and that all of the main logic is in this reusable sidecar and the shared Kubernetes resource. And so, in fact, once we have synchronization, we can also relatively easily do master election. And this is an example of doing master election in Python, where I can use my Metaparticle sync to do an election, give that election a name. The same infrastructure, the same sidecar, the same shared lock resource allows you to do master election between the different components as well. And again, I think this is like sorting. The number of people who can understand the concept of master election and the fact that, I really want to have replication for reliability, but really only one person running at a time, actively running at a time, the number of people who can understand that concept is way larger than the number of people who can successfully implement it. And so by allowing people to consume this as a concept, just like you do with sorting, I've broadened the base of people who can take advantage of this distributed systems pattern. Hopefully also broadened the base of people building reliable distributed systems, because now there is actual real synchronization and a shared implementation that we can constantly make better. Right? So part of the value of sharing isn't just the broad base, but it's actually the fact that we concentrate on a single implementation, and all of the experts come in to improve that implementation over time. All right, so I have about 3 minutes left, and replication and locking, well, replication is relatively straightforward. Many of you probably already knew how to do that. Locking is a little bit fancier, but again, I think a lot of people have sort of figured this out. I wanted to show how we can take this idea behind Metaparticle and broaden it out to a more complicated distributed systems pattern. So we take a look at something like sharding, where a particular request always goes to a specific machine. Right? This is useful if you're going to do local caching. It's useful if you want to control failure domains and things like that. This is the layout of what sharding would look like in Kubernetes. You've got a shard routing service. That's a load balancer that broadcasts all of its traffic out to the routers. Those are stateless and round-robin replicated. The shard router is the thing that's responsible for the logic of which of the specific shards should I take this request to. And so in particular, you can see that all of the green requests come in and are delivered to shard 0. All of the blue requests come in from all the shard routers and are delivered to shard 1. And all of the yellow requests come in and are delivered to shard 2. Right? So teaching someone about this is relatively complicated. You have to teach them about things like consistent hashing and other sorts of things. You have to teach them about how to build a shard router. If anyone's ever deployed something like this, you find yourself, speaking of code that you rewrite over and over again, the code in that shard router is something you keep rewriting over and over again. We want to have better reusability. I want people to be able to consume sharding as a concept. So what does this look like if you do it in Metaparticle? It's a little bit more complicated than the replication. Here's a Java example of it. I have the packaging information that I had before. Instead of replicas, I have 4 shards. And instead, I have added this sharding pattern. And this sharding pattern basically says, what's the key of the HTTP request that I want you to shard on? And in this particular case, it's kind of a nasty regular expression, so I apologize for that. But it basically says, I want to shard on the username. So all requests for a particular user should go to a particular shard. And then below it is the code that actually runs on every single server. Right? So it allows me, in the same code that I implement the server, to consume this distributed systems concept of sharding. All right, so for the final demo, I will give you an example of that. If we drop over here to this sharding, I'm going to show you the example in JavaScript. Here is roughly the same thing that was in that Java before, shard specification, the URL pattern. In this case, I'm just using the entire URL. Do the same thing. I'm running that in JS. You can see it's building the container. It's going to push it up to the Docker registry. Once the push is finished, it's going to go and deploy it. In this particular case, in the deployment to Kubernetes, it's going to look a little bit different, because now actually I'm using stateful sets. And so now I have a stateful set that's being deployed, and you can see those stateful sets starting to come up. I'm deploying 2 services, the web sharded service itself and the shard routers. And I'm deploying this replicated deployment that is my shard router. And so now if I drop into the cluster, and I apologize, I'm just a second over time, but I will be finished, I promise. Now when I do a wget, you can see that every single request I send to that request is being serviced by the same shard, right? And if I change the path, maybe now it's being served by shard 0. And if I change the path here, it's back to shard 1, right? So you can see here, with that simple annotation inside my code, in an idiomatic way, I can express and deploy the distributed system concept like sharding. Metaparticle is up on the web, metaparticle.io, github/metaparticle.io. Really encourage you to come check it out. Thank you so much for listening, and enjoy the rest of the conference.
So we have a 30-minute break, but I think there's a lot of folks in here who probably want to ask some questions. We're going to do it a little special since it's my birthday today, that I don't want to talk too much. So if you have a question, just queue up in the mic. Sound good? But I do have one from the app, if I can ask that one first.
Please, ask away.
What do you think comes after this era of APIs and microservices?
Boy, if I knew that. I mean, I think that one of the challenges of being in the middle of something is it's hard to imagine what the future becomes after that. I think a lot of patterns are inevitable. Like we went from monoliths to client server, and now we're going back, and then we went back to, so like you sort of had monoliths on mainframes, and then you went to client server with X, and then you went back to monoliths on PCs, and now we're back to client server with mobile and APIs. You know, maybe we'll decide that microservices are just too hard to understand, and we'll go back. You know, phones will become powerful enough that we'll just go back to building monoliths on phones. I don't know. I'm not sure I have a good answer to that question. Sorry.
That's OK. I think it was just more of your, your feelings.
Yeah. I think APIs are here. Actually, I honestly think APIs are here for a long time. I think decoupling is really valuable, and APIs are going to stick around for a long time. But that probably is going to sound like, whatever the quote was, like, nobody will ever need more than 640K of memory or whatever.
Exactly, right? Another question, are there plans for you to have Metaparticle kind of become more production ready? I mean, what steps are you looking at that need to be there for it to be production ready?
So it's an interesting question. Well, day 2 is really not there at all. Like, I have no idea what the upgrade story looks like in this environment. I was talking with Anders Heilsberg, actually, who is the creator of C# and TypeScript. And we were having a sort of, a conversation about whether or not Haskell was a successful language, because that's what you do when you're talking to programming languages people. And I was arguing that I thought that Haskell had not been particularly successful as a language because it is not really in widespread use. But he argued that, in fact, actually, it has been very successful because the concepts of things like lambda functions and the anonymous functions and other pieces of the things that they pushed forward are now ubiquitous. Every single programming language has anonymous functions, and the idea of being able to pass a function and things like that are now ubiquitous in programming languages. And so while the language itself didn't see widespread adoption, the concepts that it put forth became important concepts in popular programming languages. And I think if I were to hope for success, that's what success would look like. That this system is not the system that takes us forward, but it is the system that expresses some of the ideas that become important pieces in things that we build in the future. So really, I want it to be a forum for discussion and a forum for experimentation more than because I think that's the phase we're in. We're figuring out what we need to build. I don't think we have the answers, and certainly I don't have the answers. But it's interesting. So there's a startup out of Seattle called Pulumi that just launched that's doing very similar things, actually. And so I think that I'm starting to see. So for a while, I really thought I was like the crazy guy out in the woods. but I'm starting to see the signs and talking to people. I'm starting to see multiple people independently coming to the same conclusion, which I think means we're in the experimentation moment where we're going to figure out what we need to build. So, yeah.
So mentioning Pulumi, there was actually a question through the app about what's the difference between Pulumi and Metaparticle.
Metaparticle was 6 months earlier. Actually, a little bit longer than that. No, actually, I met with I meet with Joe Duffy, who's the CEO of Pulumi, a bunch because we kind of like reassure each other that we're not crazy, which probably just means we're both crazy. But I think that the difference is that for now, at least, Pulumi is really focused on the deployment part, really focused on how do I express my infrastructure as code. They don't really do this mix of application code and deployment code in the same place that Metaparticle is trying to do. I think they're focused on taking pain away from existing users of some of these YAML-ish templating languages, as opposed to, I'm really fascinated with how do we bridge CS 101 developers to become cloud-native developers. But on the other hand, I think also I have the advantage of I can kind of do a science project. And so Metaparticle is more of a science project. I think Pulumi is trying to be useful today. But I imagine that we're going to end up in a roughly similar place as time progresses. Yeah.
Yeah, and it's probably a great thing too, right? Just moving the whole industry ahead, right?
Yeah, I think that's really. I mean, and they open source too, and I think that I really feel like it's early enough that we just need to be talking a lot and collaborating on the ideas and figuring out what the right ideas are, rather than like being like, oh, you know what, you do that and we do this, and here's where we differentiate and all this sort of stuff, right? So I think that's really great. So.
2 more quick questions.
Yeah.
I don't see anyone queued up, so I'll just keep asking them.
Yeah.
My birthday
To be clear, Adam said, if you want to ask a question, the mic is right there. So just to put that out there.
Or you just love hearing my lovely voice.
I don't know.
Any advice for PaaS vendors?
Sorry?
Any advice for PaaS vendors?
PaaS vendors. So I gave this whole talk. I don't know if it's available anywhere. I gave this talk a while ago called PaaS is Dead, Long Live PaaS. And basically, my supposition, and I think it's wrong, even truer now than it was when I made it, is that PaaSes are becoming refactored on top of container orchestration. PaaSes used to be built down to the metal and very monolithic and a big choice, right? You were a Cloud Foundry shop, or you were some other Heroku shop, or it was a very monolithic decision. Because it was hard to share things between them, and because it was such a big kind of investment to deploy that cluster. I think what we're seeing as these PaaSes get refactored on top of container orchestration and on top of Kubernetes is that it's a much smaller decision. It's a decision that a team can make, as opposed to a company. And that there's way better interoperability, because like the Kubernetes service discovery layer is still there. So a service that you build in a functions as a service may actually be available to you in a 12-factor PaaS, right? And so I think that means that it's a much less intense choice. It also has meant that it's way easier to build these systems. And because it's way easier to build them, you're starting to see practitioners who are subject matter experts in the particular chunk of developer experience build PaaS, who might not otherwise have been able to, because they would have had to build the distributed system bits. So I think you're going to see an explosion of, and I think you already are seeing, there's something like 10 different implementations of functions as a service on top of Kubernetes. You're going to see this sort of Cambrian explosion of PaaSes targeted at various areas being built on top of container and container orchestration. I would say if you're not doing that and you're a PaaS vendor, you're probably doing it wrong, but I think they've all figured that out at this point. And then I think what you're just going to see is much more verticalization, because the differentiation is going to come from the developer experience and from the targeting to a particular vertical, as opposed to the quality of the distributed system, because that's going to come from the containers and container orchestration. Yeah.
Cool. And swoop! Turn around and we have questions. Go ahead.
Yeah, I have one question about basically this future thing. Because I saw your demo and I find it very interesting, but I still notice that you basically need to know, as you said, you need to know all the concepts about like how many replicas do I need sharding. Do you ever see a future where you can actually don't need that either? You can just express your vision code and then it gets deployed in a way that's most efficient.
Yeah, I mean, I think that's always kind of been, in some ways that's always been the goal of PaaS. I think there is this sort of idea that you can go to what people call intent-driven code, where you can say something like, this code, 250 milliseconds latency, 4 nines uptime. Like you give the spec for what you want your code to do as opposed to the topology that your code should be deployed in. I think we have to build these things in layers, right? I think, I think that the challenge is that when you jump to the PaaS layer, you don't build the things below the PaaS layer in a modular, decoupled way, and so you end up with these monoliths. So I think you have to build up. I think ideally we get to that place. I think it's really hard, and I think it's going to take a lot of thought and a lot of effort to build up the right layers. Right? I mean, I think if you look at sort of the development of operating systems, it used to be like you wrote directly to, there was no operating system, and you wrote straight to the machine. And over time, we've figured out what the right abstractions are to layer on top. It takes a long time to get that right. So I hope so, but I don't want to I don't want to jump too far in a single step. Yeah.
There is one concept from CS 101 which took a while to pick up with developers, dependency injection. In
Sure.
the Metaparticle experiments, have you considered configuring the container of dependency injection to be explicitly the cloud implementation of it?
Yeah, I think I have always kind of thought that the Metaparticle stuff is organized around the unit of a single microservice. And so I actually would hope that dependency injection came from something like a service mesh rather than from something that you actually put into your code. Because I feel like you want that decoupling, right? If your code knows how to inject a dependency, you probably are too tightly coupled to the dependency, right? If you're not going through a load balancer, if you're not going through some sort of service discovery. So I actually think that a service mesh is a way better way to approach something like dependency injection for microservices than getting it into the code. But I don't know. I'd be very interested to see what it would look like.
Thank you. We'll see.
Cool. I'm so sorry to do this, but I think the natives are getting restless.
Oh, no, that's fine. I'll be up here if people want to come and chat. I'll just hang out. So thank you so much.
Yeah.
Really appreciate it.
Can we do
Thanks
one
for
more
sticking
round of
around.
applause?